In this section, we're going to look at composite trigonometric functions. Before we can talk about composite trigonometric functions, let's refresh our memory as to what a composite function is. So you may have seen things like this. Let's say you were given f of x equals x plus 5. And then you were given that g of x was equal to some other function, say 2x squared minus 4. You may have been asked to find the composite of these two functions as f of g of x, or maybe you were asked to find g of f of x. Depending on which you were asked, you were either inputting the g of x function into the f function, or you were inputting the f function into the g function. Let's take a look at what this would have been if I had been asked to find the composite of f of g of x. All right, so notice that on the inside of this composite function is g of x, And g of x has been defined for us as 2x squared minus 4. So in order to do this composite function, I would need to write f of that g function, which is 2x squared minus 4. So something to notice here, in the g of x function, 2x squared minus 4 was an output. But in the composite function, that 2x squared minus 4, the g of x, becomes the input of the f function. Now, what does the f function tell us to do with the input? The f function tells us to take an input and then add 5 to it. So that's what I'm going to do. I'm going to take this input of 2x squared minus 4, and I'm going to add 5 to it. And simplifying that, I get 2x squared plus 1. That is what f of g of x is equal to. Now, if I did g of f of x, I might get a different response. But you may remember that if you take the composite of a function and its inverse, regardless of which way you go, if you do a function composed with its inverse or you do an inverse composed with the function, it always equals one thing. And that one thing is the same for trigonometric functions. If you take a function f and you compose it with its inverse, it will equal x for all domain of f inverse. Now, why f inverse? Because f inverse in this case is the inside function. If you take f inverse composed with f of x, that's also going to equal x, but that's for any x in the domain of the function, and that's because f is now the input. So let's summarize. For sine, cosine, and tangent, notice that we're starting with the original function, sine, cosine, and tangent. And then we're composing that with the inverse of each. These will all equal x as long as, this is the example of the first one, because we have the inverses on the inside, right? We have the inverses on the inside. As long as that x value is in the domain of the inverse. So the domain for the inverse for sine would be from -1 to 1, including those values. Same thing for the cosine. And for tangent, it's going to be from -infinity to +infinity. Now, let's reverse it. Now, let's do inverse sine, inverse cosine, inverse tangent, composed with their original functions. And they're still all going to equal x. But we have to make sure that those x's are in the domain of f. And earlier we said that the domain of f is going to be for the x, for sine, it's going to be from -π/2 to +π/2, including those values. For cosine, it's going to be between 0 and pi, including those values. And for tangent, it's going to be the same thing as sine, only it doesn't include the -π/2 and the +π/2. Now let's look at some examples. Evaluate the following. We have A, B, C, D, E, and F. There's a lot of parts here. But one thing I want to point out to you is that in all of these parts, I am being asked to compose the inverse with the original function. All of these start with inverses, don't they? They all start with inverses. So I need to pay attention to the rule that says the inverse of a function composed with its original is equal to x as long as we are within these values of x. So we could say, here's what our hope is. We hope that for part A, inverse sine of the sine of pi over 3, we hope that that equals pi over 3. And when I say we hope, let me just erase this because it looks a little messy. When I say we hope that that's the answer because we hope that pi over 3 is within negative pi over 2 to positive pi over 2. If you remember where those are, that puts me in quadrant 1 or quadrant 4. So if pi over 3 is in the first quadrant or the fourth quadrant, then that's a good answer. And it is, because pi over 3 I see is in the first quadrant. Now, let's look at part B. Inverse sine of the sine of 2 pi over 3. Is that going to equal 2 pi over 3? That's what we hope for. But you'll notice if you take a look at the circle, 2 pi over 3 is actually over in the second quadrant, isn't it? We would have to break through that border. So this one does not equal 2 pi over 3. So what will we do? Well, what we want to do is rewrite this composite function as inverse sine of the sine. We want to replace that 2 pi over 3 with another angle measure that is within our boundary and has the same sign. That was a mouthful. Let's just look at that again. We want to replace 2 pi over 3 with an angle measure that is within the boundary and has the same sign. Well, what is the sign of 2 pi over 3? It's the square root of 3 over 2. We see that same square root of 3 over 2 value in the first quadrant when we're at pi over 3. And pi over 3 is within our border. So I'm going to say that inverse sine of the sine of 2 pi over 3 is equal to inverse sine of the sine of 1 pi over 3. And now that that 1 pi over 3 is within that border, I can say that it equals x or pi over 3. Okay? Let's try part C. Part C says inverse cosine of the cosine of 2 pi over 3. Is 2 pi over 3 within 0 to pi? And the answer is yes, it is. So that answer is done. It's really nice when it's in there. Bam. And let me just erase a little bit here because those circles were for sine. Okay. For cosine, we are between, like I said, from 0 to pi. Okay, so we're either in the first quadrant or the second quadrant, and we saw that 2 pi over 3, sure enough, was in the second quadrant. Now, for part D, it says inverse cosine of the cosine of negative pi over 3. Negative pi over 3 is in the fourth quadrant, so that is outside the border. I need to rewrite that angle measure as an angle measure that has the same cosine. What is the cosine of negative pi over 3? The cosine of negative pi over 3 is 1/2, but that is an angle that is within our border in either quadrant 1 or quadrant 2. So if I look up in quadrant 1 or 2, I can see that I have a cosine equal to 1/2 when the angle is pi over 3. So I'm going to rewrite cosine inverse of the cosine of negative pi over 3 as cosine inverse of the cosine of positive pi over 3. And now I can say that that answer is pi over 3. Now I want to point something out to you really quick. On these ones that they weren't direct, what is the relationship between 2 pi over 3 and pi over 3? And what's the relationship between negative pi over 3 and pi over 3? Do you see it? Let me erase here. So here is 2 pi over 3, Here is 1 pi over 3. And here is negative pi over 3. The answer is that they all have the same reference angle. Reference angle is the distance between the terminal side of an angle and its closest x-axis. They all have the same reference angle. So when you have an angle measure that is not within the boundaries that you need, simply look, find its reference angle, and then find that reference angle in the quadrant that you do have your angle measure in, or within your border. Okay, so let's try another one. How about, we'll switch to tangent. For tangent, let's see here. So we have tangent inverse of the tangent of pi over 8. And for tangent, we have to be within the border of negative pi over 2 to positive pi over 2. Is pi over 8 within that border? We don't know exactly where it's at, but I know that pi over 8 is going to be a little bit smaller than pi over 6. So I think that we're good there. I'm just going to say pi over 8. Bam, I'm done. Last one, inverse tangent of the tangent of 11 pi over 9. Where is 11 pi over 9? Again, I don't know exactly where it's at, but I do know that halfway around is pi, and in ninths, pi is 9 pi over 9. Now, what that tells me is that 11 pi over 9 is in the third quadrant. And it's not only in the third quadrant, but it's 2 pi over 9 away from the x-axis. So I'm going to say, that's a reference angle, I'm going to say that the tangent inverse of the tangent of 11 pi over 9 is equal to tangent inverse of the tangent of 2 pi over 9. And let's just see if we agree with that. Let's just say that 11 pi over 9 was here, right? Let's just say it was in that third quadrant. If I go diagonal across, that's where 2 pi over 9 is. And 2 pi over 9 is going to be in that first quadrant. It is within our border. It doesn't matter that we don't know what the tangent of 11 pi over 9 is or 2 pi over 9 is. What we do know is that they will have the same tangent. And how is that possible? Well, because in the first quadrant, the tangent of 2 pi over 9 will be the sine over the cosine, so it's a positive over a positive. In the third quadrant, it's going to be those same values, but just a negative over a negative. And so we can say, it's sort of like the tangent inverse and the tangent cancel each other out, and we are left with 2 pi over 9. So the key here is, if you are dealing with an inverse of the function, and your angle measure is not within the border that you need, then what you should do is find the reference angle of that angle and use that reference angle as long as it's within the border that you want. Now let's take a look at evaluating a composition of functions where we are not dealing with a function and its inverse. We have two parts here. The first part starts with inverse sine and asks us to compose that with the cosine. The second part starts with sine and asks us to compose that with inverse cosine. So these are just the opposite of each other. All right, part A. Inverse sine of the cosine of 13 pi over 6. We're going to start with the inside of that function, which is the cosine of 13 pi over 6. Let me write this all down. So inverse sine of the cosine of 13 pi over 6. So what is the cosine of 13 pi over 6? If you know what that is, you can go ahead and write it in the parentheses. If you don't know what it is, then you might want to just draw yourself a little circle and say, okay, well, I do know that all the way around is 2 pi, and 2 pi in sixth is 12 pi over 6. So then that means 13 pi over 6 is in the same location as 1 pi over 6. So maybe I'll rewrite this as inverse sine of the cosine of pi over 6. I could write it like that. And the cosine of pi over 6 is, what is the cosine of pi over 6? It is square root of 3 over 2. And now to finish out this problem, I want the angle that produces a sine of square root of 3 over 2. And that angle is pi over 3. If you have a unit circle in front of you, then you see that up here at pi over 3 is a sine of square root of 3 over 2. All right, so that's part A. Part B. Part B says to find the sine of inverse cosine of 4/5. All right, so what does that equal? So starting on the inside, we need to find the angle. So this output is going to be an angle, right? And that angle is going to be an angle that is between, we're talking about cosine, so it has to be an angle that's between pi and 0, right? That's what the angle has to be for inverse cosine. Now, the problem with this one that I see right now is that we don't have memorized an angle that has an output of 4/5. So we're going to have to get a little creative. And so what I'm going to do is I'm going to let the angle be called theta, and I'm going to let that theta, because I know that all of what's circled here, that's an angle. So I'm going to let the angle be called inverse cosine of 4/5. Now, what that does for me is it allows me to replace that original input with theta. Now, you might be thinking, why in the world are you doing that? Let me show you. So that's going to be rewritten as the sine of theta. Now, doesn't that look nice, right? Now, how does that help me? Well, the sine, we know, is the ratio of y over r. So if we can find y and r, then we have it. So, do we know anything about y and r? Well, if I go back to how I defined theta, theta is equal to inverse cosine of 4/5. Another way to write that would be to say that the cosine of that theta must equal 4/5. Isn't that true? If the angle is equal to inverse cosine of 4/5, then the cosine of the angle, the output, has to be 4/5. And what we know about the cosine is that it is equal to x over r. Isn't that nice? All right, so I think we know what r is, don't we? We know that it's 5. So if we can find y, then I think we've got this one solved. So how are we going to find y? Well, we know that x squared plus y squared is equal to r squared. So 4 squared plus y squared equals 5 squared. So if I solve this for y, and I'm running out of room a little bit, so I'm going to leave this up to you to do, I think that I end up with a y value that is equal to, or a y squared value that is equal to 9. And when I square root both sides, I get plus or minus 3. I didn't show you all my steps there, but I think you can do that arithmetic. Now, here comes the question. Is it a plus 3 or is it a minus 3? Well, let's go back up to when we defined the angle. We said that angle had to be between 0 and pi, which means it's in the first quadrant or it's in the second quadrant. With an output of 4/5, that's a positive output, that forced us into quadrant 1, didn't it? So if we're in quadrant 1, then that means that my y value has to be positive. So this final answer is that the sine of cosine inverse of 4/5 is equal to 3/5. And we'll do another one of those here in just a second, because that feels maybe a little confusing, but I think if you go back and look at how we define things, it'll make more sense. So here is another one like the last one that we saw. Part C of this problem says sine of inverse tangent of 7/4. All right, so I'm going to say that the sine of inverse tangent of 7/4 is equal to something. And so what we're really saying, we know that inverse tangent produces some angle, right? We looked at this before. This produces some angle, and how about if we just go directly into calling that angle theta? And what we know about that angle theta is that it has to be between pi over 2 and negative pi over 2, right? So if we let me erase that for a second. Let's let theta equal inverse tangent of 7/4, then we can say that sine of inverse tangent of 7/4 is the same thing as the sine of theta, because we've defined theta as being equal to all of this, right? So we're just substituting it. Now again, how does that help us? Well, because we know that sine is simply equal to y over r, isn't it? Simply equal to y over r. So if we can find y and we can find r, then we're in business. Okay, so let's keep going with this. We said that theta is equal to inverse tangent of 7/4. That's the same thing as saying that the tangent of some angle is equal to 7/4. And the way that that helps us is because we know that the tangent is equal to the ratio of y over x. So we also know that x squared plus y squared is equal to r squared. So I can say that 4 to the second plus 7 to the second is equal to r to the second. And I'll let you do this arithmetic. I got 16 plus 49, and that equaled 65. So when I square root both sides, I got that r is equal to plus or minus the square root of 65. Now, is it the plus or is it the minus? Well, we have to go back to how we defined theta, right? We said theta is equal to inverse tangent of 7/4. And because theta has to be between pi over 2 and negative pi over 2, that puts us in quadrant 1 or quadrant 4. The only quadrant where we're going to see a positive tangent is going to be quadrant 1. And in quadrant 1, we would expect all the values to be positive. Now, did I have to think about that for r? Not really. I got a little ahead of myself. R is the radius, right? And so the radius in a circle is going to be a positive distance. So that's going to be positive square root of 65. But that does tell me that the y value is going to be, what did we say that y value was going to be? 7. So this is going to be 7 over the square root of 65. And of course, if possible, you should always rationalize your denominator. So I'll multiply numerator and denominator by the square root of 65 to get a final answer of 7 times the square root of 65 over 65. And that is what the original problem is equal to. Let's look at one more example where we're asked to solve a trigonometric equation. So an equation is simply something where you have an equal sign and you're being asked to solve for whatever variable you happen to have. It's no different than from an algebra class where maybe you're asked, to solve 3x plus 2 equals 11. You would subtract 2 from both sides and then you would divide by 3, and I think you end up with x equals 3 as a solution. Okay, same idea here. To solve for part A, it says 2 times inverse sine of x is equal to pi. So the first thing that I'm going to do is I'm going to divide both sides by 2. And that gets me inverse sine of x is equal to pi over 2. Now, the reason why I did that step is because ultimately I want to get this x by itself. But I can't get that x by itself until I get the thing that's connected to the x by itself. So that x is trapped inside this inverse sine function. So how do I get rid of inverse sine? Well, what I can do is I can take the sine of inverse sine, because if you remember when we talked about composite functions, if you take a function and you compose it with its inverse, what happens? It's almost like they cancel each other out, isn't it? So you're left with x equals, now if I take the sine on the left, I have to take the sine on the right. Now make sure that when you do this step that you write the sine of pi over 2, right? Writing pi over 2 and then sine, you're not multiplying these two, right? That's no good. You're taking the sine of pi over 2. And what is the sine of pi over 2? Think about your circle. You go up to pi over 2, you're at the point 0, 1, therefore the sine is 1. All right, so x equals 1 is the solution. Writing that as a solution set, we would say the squiggly set notation 1, and then we'd close that off. All right, part B. I want to get the x by itself. Before I can get the x by itself, I need to get the inverse cosine of that argument by itself. So I'm going to divide both sides by -3. Divide by -3. Divide by -3. That's going to get rid of that -3. I'm going to be left with inverse cosine of 3x equals -pi over 3. Now pay attention to the fact that when I divided by -3, the only thing that -3 divided into, this -3, was the -3 on the outside. Nothing is going to happen to this 3x until it's out of the cosine, the inverse cosine. It's not being touched until I do that. All right, so now what? I need to get rid of that inverse cosine. So I'm going to do the same thing as you just saw me do. I'm going to take the cosine of the left and I'm going to take the cosine of the right. So I'm going to get cosine of inverse cosine of 3x. That's going to equal the cosine of -pi over 3. Cosine and cosine inverse undo each other. So I'm left with 3x. What is the cosine of -pi over 3? Well, -pi over 3 is in the fourth quadrant, but you could also think about the fact that the cosine is an even function, isn't it? Cosine is an even function, which means that the cosine of a negative angle is equal to the cosine of that same angle but positive, right? We've learned that in previous sections. So I can rewrite this if I feel uncomfortable with negative angle measures. The cosine of -pi over 3 is the same thing as the cosine of +pi over 3. What is the cosine of pi over 3? Think about where pi over 3 is. The cosine is going to be 1/2. Now, if I divide by 3, and maybe for the 1/2, instead of dividing by 3, I multiply by 1/3, that's the same thing, right? I'm going to be left with x equaling 1/6. And as a solution set, I'm going to say the squiggly set notation, 1/6, and then I'll close that off. Keep in mind, and I'll leave this up to you to do, if we believe that the value that solves these equations, I've circled them here, if we believe that those are true, I should be able to substitute those back in, shouldn't I? I should be able to substitute those back into the original, which my originals look pretty messy, but I'll leave that up to you to do. Substitute them back in and make sure that they really do equal what they're supposed to equal.